Good morning all. My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about a model of the image degradation and restoration process. So, what is the image degradation and restoration? So, a restoration of the image. A restoration attempts to reconstruct or recover an image that has been degraded by using a prior knowledge of the degradation phenomena. A restoration techniques are oriented towards modeling the degradation and applying the inverse process in order to recover the original image. So, first we are going for the degradation and the restoration. What is the difference? We will discuss now restoration with the degradation. So, restoration attempts to reconstruct or recover of an image that has been degraded by using a prior knowledge of the degradation phenomena. So, restoration techniques are oriented towards modeling the degradation and applying the inverse process in order to recover the original image. So, what is the use? When degradation is a process. After this one, we are restored with original image. That is restoration. So, degradation means we are applying some technique. What is that? We are applying some transformation technique. We are applying some process. The process of converting from one image to the another image. That is a degradation process. So, first input image is there, output image is there. So, what is happening means between the input and output, degradation process is going on. Degradation process is going on between the input to the output. So, what is the degradation? After the completion of degradation process, the output image is restored with original image. Restored with input. Restored with input. That is the value of output value. So, what is the image restoration? Image restoration attempts to reconstruct or recover of an image. It has been degraded by the degradation phenomena. That is a definition of the restoration. And it is the enhancement. It is the image enhancement. The ultimate goal of restoration, technique is to improve an image in some predefined sense. And it's like enhancement technique, restoration technique can be performed in the spatial domain and the frequency domain. So, noise removal is applicable by using the spatial domain filtering, whereas deblurring is performed by using frequency domain filtering. So, image restoration, it is a process for image enhancement. So, in the image enhancement, the ultimate goal of the restoration technique is to improve of an image in some predefined sense. Like enhancement technique, restoration techniques can be performed in the spatial domain and the frequency domain. But what is the example I am taking for restoration technique? Noise removal is the application using the spatial domain filtering, whereas deblurring is also performed using the frequency domain filtering. It is the examples for image restoration. So, what is the model of image degradation and restoration? We are taking one equation between the relation between the image degradation and restoration. So, image degradation is a process that acts off an image of f of x, y, and through the degradation function h and additive noise nu of x, y. So, the result of degraded image g of x, y is that g of x, y is the degraded output. Degraded input image is equal to h of x, y into f of x, y plus nu of x, y. So, what is a nu here? Noise. Or that is also called additive noise. So, when degraded image or degraded function g of x, y equal to h of x comma y into f of x comma y. F of x comma y is the input image. It is the transformation function or transformation image. Input image with the transformation function h of x comma y into input image f of x comma y plus with the noise, additive noise, that is called degraded input. So degraded function g of x comma y equal to a transformation function h of x comma y, input function f of x comma y plus noise, additive noise, that is a nu of x comma y plus nu of x comma y. Here h of x comma y is the spatial representation of the degraded function. The symbol is star. It indicates a convolution function. So in the previous we discussed here what is the h of x comma y, where h of x comma y is the spatial representation of the degradation function and the symbol star indicates a convolution function. That note, we have only degraded image, that is the g of x comma y, only degraded image g of x comma y. The objective of restoration is to obtain an estimate of the original image, and we have to estimate the closer possible of the original input image, and the more we know that what is the h and nu of the closer will to the f of x comma y. It is the input function or image, input function or image. So the objective of restoration is to obtain an estimate of the original image, and we have to take the closer possible values of the original image. That is more know about the h and nu. Nu already we know that noise, h is the transformation function, it is the input function f of x comma y. So when we are going for the image restoration, it is a process of recovering an image that has been degraded by some knowledge of degradation function capital H and the additive noise term mu of x comma y. But the restoration is the degradation is modeled and its inverse process is applied to recover the original image. So here f of x comma y is the input image. This input image is going to the degradation function h. So here nu of x comma y is the additive noise. Additive noise is added to the degradation function h, that is the g of x comma y. After the noise, the equation is a g of x comma y. It is g of x comma y. The restoration filter input is a g of x comma y, output is a f dash of x comma y. So what are the methods we are applied means degradation technique and the restoration technique. What is happened here? F of x comma y equal to f dash of x comma y. F of x comma y equal to f dash of x comma y. So input and output both are same, but what is the difference means it is the noiseless. Input is the noisy. So noisy image is converting to the noiseless image with the help of degradation and restoration functions. So image restoration and degradation model, it is one example. So finally, image restoration is the process of recovering an image that has been degraded by some knowledge of degraded function h and the additive noise nu of x comma y. Then restoration, degradation is modeled and the inverse process is applied to the recovering of the original image. That is the f of x comma y equal to f dash x comma y. Degradation function is h, noisy function or additive noise nu of x comma y. After the noise, so g of x comma y is the noisy image. So how we are reducing the noise image means with the restoration filter noiseless image, that is a f dash of x comma y. So here g of x comma y equal to noisy image, f dash of x comma y is equal to noiseless image. So what is the process means degradation restoration process is applied. It is the objective of the image restoration. The objective of image restoration is to obtain an estimation of the original image f of x, y. Original image is the input image. Here, some knowledge capital H and nu of x, y to find the appropriate restoration function that the output image f dash of x, y is closer to the original image of f of x, y is possible, since it practically not possible if very difficult to complexity or exactly restore the original image. So terminology is that g of x, y equal to degraded image, f of x, y equal to input image, f dash of x, y equal to recovered or restored image, mu of x, y equal to additive noise function. So what is the spatial domain equation? G of x, y equal to h of x, y into f of x, y plus mu of x, y. So what is g of x, y here? Degradation function. Here degraded image with h of x, y equal to f of x, y is equal to input image. So degraded image g of x, y equal to h of x, y. It is the noisy. So input image with noisy image, that is the h of x, y. You can see here input image f of x, y, degraded function h of x, y, and the noise function with noise equal to g of x, y. The restore function is f dash of x, y. Same like this here. G of x, y means output function. G of x, y is the degraded function or output function. G of x, y equal to h of x, y, that is a degraded input, with f of x, y input image plus noisy image, noisy function mu of x, y. It is a total equation, but here it is the objective of registration to estimate the original image f of x, y with knowledge of h, but here noisy function is mu of x, y, and the f dash of x, y is the output image. So finally the restoration or restored output image is equal to f dash of x, y. Output image. So it is the equation for spatial domain. Here I am taking the equation for frequency domain. So what is the frequency domain means? What is the transformation technique applied? Fourier transform. So what is the equation for the Fourier transform? Equal to capital G of u, v equal to capital H of u, v into capital F of u, v plus capital N of u, v. So same as it is in the previous, G of x, y is the, what is the G of x, y? Degraded image. H of x, y is the function, f of is the input image, capital N of u, v is equal to noisy. So degraded image output capital G of u, v equal to capital H of u, v into capital F of u, v plus N of u, v. So the restoration filter capital R of u, v is that f dash of u, v equal to capital R of u, v into capital G of u, v. So f dash of u, v output function f dash of u, v, it is also called restored image, restoration function of the image, that is a f dash of u, v equal to capital R of u, v into capital H of u, v into capital F of u, v plus R of u, v into N of u, v. So finally what it means? F dash of u, v equal to F of u, v. So output function, output image equal to input image. It is also called restored image. F of u, v is also called restored image. So F of u comma is also called a noise image. F dash of u comma is also called noiseless image. So here the restoration filter R of u comma v is the reverse of degradation function, and the capital H of u comma v, and neglecting the term noise, then capital H of u comma v is the linear position invariant function. So what are the approaches for the image degradation and restoration? There are various types of restoration filters we are using to approaching the restoration process or the image. We assume that H is the identity operator and will deal only the degradation function due to the noise. So what are the degradation types? So types of image degradation. Degradation comes in many forms such as motion blur, noise, and camera misfocus. In case like motion blur, it is possible to come with at very good estimation of the actual blurring function and undo the blur to restore the original image. So how we are degrading the original image? So blurred image is converting to the blurless image. Oh, means there are so many types of processes, techniques we are applying for the image degradation. Here one technique is with example we are discussing, that is a degradation comes with many forms such as motion blurring, noise, and a camera misfocus. Okay, suppose if I am taking the camera problem, otherwise motion blurring. So or noise. So camera problem or motion blurring or noisy problems. These are the problems. Those are I'm calling as a degradation functions. But we are overcoming these problems. What are that means? Motion blurring, noise we have to reduce, and the camera misfocus we have to reduce the problems. So these are the degradation processes we are reducing with the techniques. Then we will get the f dash of x comma y. So in case of motion blur, it is possible if I am taking the motion blur. So what is the problem? How we are achieving solution for this one? Solution for this one. So it is possible to come with a very good estimation of the actual blurring function and undo the blur with the restoration of the image. So motion blurring is a solution with undo option with the restoring of the original image. And another technique for the image restoration, various methods available for image restoration such as inverse filtering, VNR filtering, constrained least square filtering, blind deconvolution method, etc. So these are the various methods for image restoration. That is a inverse filter, VNR filter, constrained least square filtering, blind deconvolution methods. So these are the so what are the image restoration processes or methods? Inverse filtering, VNR filtering, constrained least square filtering, blind deconvolution methods. So these are the four methods we are using for the image restoration. And some of the methods are either linear or non-linear methods to remove the noise and blur of the images. Okay, in the previous we discussed noise and blurring. Okay, camera problem, blurring of the motion, or blurring or the noise. These are the three problems we are getting. So when remove the noise, it is one problem, and the blurring is another problem. So 1 and 2 are the problems we are facing with the image. So how we are overcoming means we have to either linear or non-linear method to helps to remove noise and the blurring of the original image. So linear and non-linear linear or non-linear technique we are applying to remove the blurrings and remove the noises. So image restoration is the process of recovering the original image by removing noise and blurring from the image. So blur is a difficult to avoid in many situations like photography, remove motion blur caused by camera, shake, radar image processing, and remove the effects of image system responses. Okay, so noise noise we are easily overcoming, but so noise we can easily overcome, but blur is difficult to overcome. Why? Because it is to avoid many situations like photography. In the photography, in the remove of motion blur and camera shaking the camera, radar imaging, and remove the effect of image system responses. These are the very very difficult conditions to avoid or to remove the blurrings in the original image. So these are the references of the image degradation and restoration process. So another one is a frequency domain filters we have to use. But here the frequency domain, the image is converting from spatial domain into the frequency domain. It is used for image enhancement for the spatial functions. But a fast Fourier transformation is a tool of the frequency domain used to convert the spatial domain into the frequency domain. But smoothing of an image, low pass filter is implemented, and the sharpening of the image, high pass filter is implemented. When both the filters implemented, we are analyzing ideal filter, butterworth filter, and a Gaussian filter. So so frequency domain filters are two types: low pass filter and high pass filter. But in the low pass filter, using smoothing, high pass filter using sharpening. So this is a different transformation technique. Different transformation techniques are using. But in the frequency domain, it is the digital image converting from the spatial domain into the frequency domain. Okay, spatial domain into the frequency domain, then converting to the two forms: low pass filtering form, high pass means smoothing and sharpening. But in that frequency domain filtering, we have to convert the spatial domain into the frequency. Smoothing is the low pass filter and the sharpening is the high pass filter. Both filters are implemented. Both are implemented when to analyzing the ideal filter, butterworth filter, and Gaussian filters. It is one example for low pass filter. It is another for high pass filter. So high pass filter is used for passing high frequencies, but the strength of the frequency is lower compared to the cutoff frequencies. Okay, it is an equation for high pass filtering. H of high pass filter equal to 1 minus H of low pass filter. It is one example for original image butterworth. It is a input original image. Okay, it is a butterworth filter figure. Here, mask is applied for Butterworth high pass filter, Gaussian high pass filter, and ideal high pass filters. Okay, it is the equation for ideal high pass filter. Ideal means 1, h of e comma equal to 1. When it is 1 means d of e comma v is greater than d naught when it is 1. If it is not an ideal, when it is called 0. If d of e comma v less than or equal to d naught, that is the ideal high pass filter. IHPF cutoff frequencies I am applied for this one. So how we are applying the cutoff frequencies we can discuss in the next slides. So these are the two coordinates e comma v with the h of e comma is a function. Okay, it is an ideal high pass filter. Ideal high pass filter. Okay, it is a ideal high pass filter image. It is the radial cross section. It is one example for ideal high pass filter with the frequencies to the circle of radius d0 while passing without the attenuation. So it is a cutoff frequencies with 15, 30 and 80. These are the cutoff frequencies. Okay, what are the effects of ideal high pass filter? Is ringing effect, edge distortion. That is the distortion with the thickened object boundaries. Both effects are decreased with the cutoff frequencies. Next one is a Gaussian high pass filter. It is a cutoff frequency with the distance of d0 is applied. Okay, it is one example for Gaussian high pass filter. It is an input image. It is a Gaussian high pass filter with the image, and it is a radial cross section, and it is a filtering function with a mask. Okay, it is one example of sharpening frequency domain filtering with the cutoff frequencies 15, 30 and 80. So it is an equation for S of x comma y. Spatial domain filtering S of x comma y equal to I dash of x comma y plus R dash of x comma y, and output function g of x comma y equal to exponential of S of x comma y. So when I am using exponential of I dash of x comma y into exponential of R dash of x comma y, that is the I naught of x comma y into R naught of x comma y. Here I naught and R naught are the, I naught is the illumination and R naught is the reflectance component. So overall model of the block diagram we will look as f of x comma y input image, logarithmic function, fast to Fourier transform, capital H of x comma y, inverse fast Fourier transform, exponential function, g of x comma y, output function. So you can see here we are applying exponential function. That is an exponential function. Why we are taking exponential function means for g of x comma y. This exponential function is for g of x comma y. Okay, it is the overall block diagram. It is a frequency filtering. It is an example for discrete function of m points, and it is a discrete function of twice the bond m points and 2 m points. It is an example for low pass filter and high pass filter. It is a restriction effect of creates end-to-end convolution mask h bar with the Fourier transform. H bar of u comma y equal to 1 by n into summation x equal to 0 to n minus 1, y equal to 0 to n minus 1, h dash of x comma y into e power minus j 2 pi into ux plus vy by n. So u comma v equal to 0, 1, 2, so on n minus 1. The objective to find the coefficients h dash of x comma y such that e square equal to summation u equal to 0 to n minus 1, v equal to 0 to n minus 1, h dash of u comma v equal to h of u comma v whole square. So here g of h dash of u comma v is the Fourier transform function with applying the mask. Fourier transform is for applying the mask. So when I am using a Fourier transform for filtering functions. For the filtering functions, we are using Fourier transform h dash of u comma v. So when I am using the filtering means definitely we have to use mask. Okay, these are the filtering functions. Capital H of u comma v with 0 when u of e comma v m by n comma n by 2 if it is 1 when it is otherwise condition. F of 0 comma 0 is a 0 and leave all the frequencies components such as filters is called notch filter. It's the constant function with hole and notch of also origin. So these are the functions of. So these are the sharpening frequency filters with examples. So we discussed today a model of the image degradation and restoration function. So image degradation restoration function, what is the definition for the image restoration? It attempts to reconstruct or recover of an image that has been degraded by a degradant phenomena. An image with enhancement technique, the ultimate goal of the restoration technique is to improve an image in some predefined senses. But like image enhancement technique, the restoration techniques can be performed in the spatial domain and frequency domain. In the spatial and frequency domain also we are using the restoration and degradation techniques. But finally, what we are calling it is an enhancement technique. Example I'm taking, what is the use of enhancement technique for spatial domain and frequency domain is that we are using the noise removal is applicable using spatial domain filtering, whereas in the deblurring of the performed using the frequency domain filtering. Okay, so what is the model of the image degradation and the restoration function? So image degradation is a process that acts of an image, input image f of x, y through a degraded function h and the additive noise nu of x, y. The result of degradation function g of x, y is that g of x, y equal to h of x, y into f of x, y plus nu of x, y. So already we know that g of x, y is a degraded input. So what a degraded equation with what we are adding here means transformation function we are adding, input function adding, and noise is also added. That is a additive noise. So h of x, y is the transformation function, f of x, y is the input image, nu of x, y is the additive noise is applied. So here h of x, y is the spatial representation. It is a spatial representation. H of x is a spatial representation of the degradation function with the symbol star, and that is a multiply symbol indicates a convolution function. But here degraded image, what is the degraded image here is g of x, y. So what is the objective of the restoration function is that we are estimating the original image. So for the final possible original input image is the capital H with nu. The closer will to the f of x, y equal to input function or image function. So f of x, y is the input function with the degraded function capital H with the noisy function that is added. So that is a g of x, y. What is the noisy function here? Nu of x, y. So what is the input for the restoration function means g of x, y means noise with input function f of x, y with the degraded function capital H of x, y. So what is the output function is f dash of x, y. So here so finally f dash of x, y equal to f of x, y. So here f dash of x, y is the restoration or restored image. So it is a restoration, that is a f dash of x, y. So what is the degradation means f of x, y. So f of x, y equal to f dash of x, y. When degradation with restoration, it is the image with restoration and degradation functions. So another equation is the g of x, y equal to h of x, y into f of x, y plus nu of x, y. Here g of x, y already discussed degraded image. H of x, y is the degraded function h of x, y. F of x, y is the input or original image with the nu of x, y is the additive noise function. So the frequency domain or frequency filtering, that is using Fourier transformation capital G of e, same. Here we are applying the transformation function, that is a Fourier function. We are applying to the spatial domain, that is a frequency domain. So Fourier transform of g of x, y is a spatial domain function. When applying the Fourier transform of g of x, y is equal to capital G of x, y. So that means for the spatial domain, I am applying the Fourier transform technique to the spatial domain. That is the Fourier transform of spatial domain function is the frequency domain. It is the frequency domain. G of x, y is the spatial domain function. Capital G of e, y is the frequency domain function. Okay, we are applied Fourier transform to the spatial domain, that is the frequency domain. So what are the approaches to getting the image restoration? What are the techniques we are using for the image degradation and restoration? So degradation comes in the many forms such as motion blurring, noise, and camera misfocus. So these are the three major types of the problems we are in the degradation process. So how to overcome these degradation uh, problems with the Fourier transform technique, with the transformation techniques? Which type of transformation technique or which type of filtering we are using to overcome these problems? Motion blurring is the possible to come with a very good estimation of the actual blurring function with undo problem. Undo is the solution for the restoration of the blurring image with the original. And the approach is to study based on a various types. H is the identifying operator and deal with the degradation due to the noise. Okay, what are the image degradation functions? Motion blurring, noise, and camera misfocus. And what are the restoration methods? So image restoration such as inverse filtering, Wiener filtering, and constrained least square filtering, blind deconvolution methods. So these are the image restoration methods. So the methods to linear and non-linear techniques are using for removing the noise and blurring of the image. Okay, linear and non-linear methods to helping the removing the noises and blurring the images. So another is a image restoration is the process of recovering the original image by removing the noise or blurring the images. Okay, but noise is easily removing, but blurring is difficult to overcome. But to avoid the situations of the blurring of the images, we have to proper camera usage of photography, and the removal of blurring is caused by camera shakes and radar imaging to remove the effect of image system by response, etc. Okay, these are the references for the image modeling, image degradation, restoration process. So it is a final block diagram of image degradation and restoration process. F of x, y is the input function. The degraded function is applied to the f of x, y, and noisy function is Gaussian noise is added to the h of x, y. That is called g of x, y. Final restored filtering restoration output is a f dash of x, y. So here degradation and restoration process is applied to this function. It is the process of image degradation and restoration process. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.